Compress the dictionary, not the code. Sparse autoencoders decompose a neural network activation into a sparse combination of interpretable features, but they learn a dense decoder matrix that balloons as the feature count grows. Expander sparse autoencoders, from a single independent researcher, replace that dense decoder with the adjacency matrix of a bipartite expander graph, so each feature touches only a handful of residual stream dimensions. The result, 293 times fewer learned weights while keeping 84% of the reconstruction quality. Decoder support structure is a design axis no one had pulled. The forward pass. Start with a residual stream activation, h in r to the m. Build the decoder as w_dec equals v masked by m times a per column normalizer. M is a left D regular expander mask. Every column has exactly D1s among M rows, sampled once at init. Tie the encoder to the decoder transpose. Pre-activate, keep the k largest signed values via top k, 0, the rest. Only the D times n non-zero entries of V receive gradients, so the parameter count drops from 2mn to dn plus n plus m. The matching pursuit correlation step becomes a gather and reduce over dn entries instead of a dense mn product. Compress the dictionary, not the code. The gap it fills. A standard sparse autoencoder stores m times n decoder values. At 40,000 features on a 2,000 dimension residual stream, that is, 80 million weights just for the dictionary. Expander SAEs cut that to d times n. With d equals 7, that is, 293 times fewer values, regenerable from a single 8-byte seed. And the sparse coding problem, MNK, is untouched. The compression lives entirely in the decoder support. What drives the gain on table 2, it is not sparsity alone, and it is not parameter count, it is support diversity. The control, a clustered sparse decoder, same M, N, K, D, but every column forced into a disjoint row block. At d equals 200, its dead feature rate climbs to 6.2% against expander's 0.7, with pruned dense at 0.4 and full dense at 0.6. A 9 times blowup in dead features at an identical parameter count. The expander's overlapping, diverse support is the active ingredient. Now the matched parameter reversal on table 3. Train a dense SAE at reduced n to match expander's parameter count, and on the trained encoder, dense wins by up to 0.12 cross entropy. But swap the trained encoder for iterative OMP on the same frozen decoders, and the gap collapses. At d equals 7, OMP gains 0.118 on llama. At d equals 30, the dense advantage shrinks from 0.06 to 0.007, and on Quen, expander pulls slightly ahead. The apparent dense win was an encoder amortization effect, not a decoder quality difference. Here is the structural payoff. Before, a dense decoder, every feature fans out to every residual dimension, a solid mat of connections, millions of weights stored on disk. After, an expander decoder, each feature touches only d of those dimensions, a sparse, regular, overlapping graph, the same coverage with a fraction of the wires. The code is still k-sparse, the recovery problem is unchanged, only the dictionary got compressed, the features stay interpretable on table 10. At d equals 7, 81% of expander's features are genuinely novel, activation jacquard below 0.1 against a dense reference, falling monotonically as d grows. A blinded 2LLM judge coherence study, Claude and GPT-4o, gives d equals 200 a 3.72, statistically indistinguishable from dense's 3.59. A different but still meaningful decomposition. 5 honest caveats. First, at matched parameter count, a reduced n-dense SAE beats expander on the trained encoder. That gap is encoder amortization, largely closed by OMP, but it remains at deployment. Second, the worst-case identifiability certificates sit well above the threshold across the trained grid, so the theorems motivate the architecture, they do not certify the experiments. Third, late layer failure happens for every architecture, dense included, so it is not expander specific. Fourth, seed instability at the storage extreme, one of 3 seeds diverges. Fifth, scale only goes to 3 billion parameters. Cite the design axis, not a deployed replacement. Compress the dictionary, not the code. Expander sparse autoencoders replace a dense decoder with a D-regular expander mask, cutting learned weights by up to 293 times at 84% of dense quality, while isolating support. Diversity, not sparsity, as the active ingredient. Subscribe for the next breakdown.